Hey guys, I'm on Tutor here, and today we're going to be going over some AP Physics 2 electricity stuff, and specifically Kirchhoff's laws. So, with Kirchhoff's laws, it's kind of difficult at first. Once you kind of get the hang of it, understand what you're doing, it becomes really easy. It's not really math intensive. It's more like kind of annoying to do, though. Like you'll see, especially with this problem, that it gets pretty annoying. But it isn't all bad. So I hope I'll kind of show you guys that today and how to do these problems. So first of all, let's go over kind of just what Kirchhoff's laws are first, and so we can implement them. First, we will have the junction rule, which is saying that a current going into a junction will equal the current coming out of that junction. So to show you with a specific example, if we use this problem we have here, the current that'll go into this junction, we'll call it I1, and then so two currents will come out, I2 and I3. So what that basically means is I2 and I3 will equal I1. So I1 is equal to I2 plus I3. And that's kind of like, just think about this kind of, well, another way. Let's say we have two rivers and all of a sudden they are divided. So they break up. So like something like this. Let's say there's a big rock here that makes it go this way. And let's say it goes like this. The total water flowing is still the same. It's just flowing in different directions, right? So that's going to mean that, oh, the total water here is the water that goes here and here. So that's kind of how that works. And you can only use the junction rule one. You can use it one less time the amount of junctions you have. So here in this problem, you'll see we have two junctions. We have one right there and one right here. So we can only use junction rule once. And that'll again become a little more apparent when we actually when we actually solve this problem, and you'll see. Um, the next one is going to be the loop rule, and that's saying basically just in a loop, the total voltage drop will be the whole voltage. So kind of, if we when we start at the battery, and you'll see this more in when we do problems, as you go and progress along through your loop, once you get back to this battery, your total voltage at that point will be zero. So you'll see again when we write the Kirchhoff's equations to solve these, kind of where that's coming into play. So let's kind of just get started real quick. I'll start with the harder one and then show you that they're all not as bad. So with the next one on the right, it's a lot easier, and kind of you'll see what's going on. So the first thing we have to do in Kirchhoff's laws and approaching these problems is, well, determine first if you need to use it. And in any problem where there are more than one battery in a circuit, you're going to have to use it so far. So you see here we have one, two batteries, so Kirchhoff's laws is necessary here. So let's do it. So first, we need to identify our currents. It really doesn't completely matter. You kind of just want to put them around a junction. So you want to do kind of how I did earlier. I1 going here, I2 going there, and I3 going here. And we're going to solve this by using a system of equations, and you need as many equations as you have currents. So we have three currents here. We will do three equations, and I'll show you those are in a second. But let's say we had a circuit like this. Let's say it was like, oh, there's like one here, one here. There'd be currents flowing this way, this way. There would be a lot more than three, like, what's it called? How do you say it? Three more currents flowing. So you need three more equations, more than three equations, is what I should say. So let's get started. So first, our first equation will be our junction rule, which is going to be I1 is equal to I2 plus I3. That's kind of just a given. That's the first and the easiest equation. Next, we're going to start using our loop rules. So what I like to do is I like to go around well, you start the battery no matter what, but I like to start going with the voltage being positive, so this way. And the way I know the voltage is being positive here is because I look at the battery and I see like, oh, it's getting bigger. So that's how I know to go this way of clockwise. With this battery, it's going to be the same thing because I want it to be positive. It doesn't matter if you flip it. Like, it won't matter if you were to do, let's say, this way. It's kind of just a matter of personal preference, and I'm just a bigger fan of making the voltage positive. But again, you can try this different ways, and you can see. We'll start with our top loop. So let me write top loop. So we're going to start here at our battery with 20 volts. And then as we're gonna progress through this resistor, right? And what you'll notice if you kind of backtrack this I1, you'll see that we're going along I1, which means that we're going to put a negative the 30 ohms and I1. I'll drop units after these equations out just to make the math part easier. Um, and the reason it's negative is because we are flowing with the current and through a resistor. Let's say, no, I'm sorry, we are flowing through the current with our loop. If our loop and our current both like go together in the same direction, the voltage drop will be negative. And if our loop rule is going against the current, which you'll see in a second, then it's positive. So after that, after we pass through the 30 ohm resistor, we get to this 5 ohm resistor. And it's going to be with I2, so we're going to do 5 ohms I2. And then we get to this battery, and notice how we're kind of getting smaller. So it's going to be it's going to be minus 10 volts. And then we're back at the battery, so it's going to be equal to 0. So I'm going to erase that kind of writing I did there just to make it a little more clear, just for the bottom at least. So now we're going to start at the bottom battery. So I'm going to write this bottom bat. No, I'm sorry, bottom loop. My bad. So we're going to start with a positive 10 volts. And if you're wondering, oh, why is it positive here and not positive in that other equation? Because remember, we're starting here and we're getting bigger. We're going with our loop. With the other one, we were going against our loop and we were going that way. So that's just why it's positive here. I could easily flip the way of this loop and like put a negative there, but I would rather have it be positive. So now we're going to go to this 5 ohm resistor, and you'll see the current I2 is flowing against our loop. Like if the current's flowing this way, our loop's flowing this way. That means we're going to add. So it's going to be 5 ohms I2. And so that's where I said it will come in later. But yeah. And then we'll keep going. We get to this 20 ohm resistor. We're going with I3 here, so it's going to be minus 20 I3. And then we're going to get back to the battery. So we're going to get, oh, I don't know why I did that. Sorry, guys. And that's going to be equal to 0. So now, let me just erase this kind of up. And we have our 3 equations. We have 3 currents, 3 equations. And now is just the math part. This is the physics part. Getting these. Now it just becomes math and like how you can do it. So the way I personally like to do it is you'll see I2 is in both these equations. I like to solve for I3 and I1 in terms of I2 and then plug that into here. That's my approach to kind of these problems. Maybe you see a better one. It's how you see fit. Now it's basically just become a math problem. So let's start. And this equation, first of all, stop that, can be simplified. So we'll take this down here to 10 volts minus 30 I1. Sorry, no, not II. Minus 30 I1 minus 5 I2 equals 0. And then I write the bottom one, 10 volts plus 5 I2 minus 20 I3 is equal to 0. So now I'm going to isolate I1 and I2. And I'm going to get I1 is going to be equal to 10 minus 5 I2 all over 30. And I3 is going to be 10 plus 5 I2 all over 20. So if you're wondering where these came from, just look here and look what I did. I have just isolated, I'm sorry, not the whole thing. I have isolated I1 and I3 to get them in terms of I2, and now I'm going to plug them into my junction rule. So I1, our new is 10 minus 5 I2 all over 30. It's going to be equal to I2 plus R10 plus 5 I2 all over 20. So now this is pretty easy to solve. I like to just get rid of the denominator. I just do it out. So we're going to have 10 divided by 30. It's going to be 0.33 minus 5 divided by 30. So divided by 30 is 0.167. I'm gonna go to a few more decimal places because last time I did this, I went to 1 and I got a few decimal points off the actual answer. So, but that honestly was just a rounding error. So this is I2 is equal to I2 plus this is 0.5 plus 5 divided by 20, 0.25 I2. So now we're just going to isolate the I2s again. We're going to move them all over. So first we're going to do 0.33 minus 0.5. We're going to have negative 0.17 is equal to 1 plus 0.25 plus 0.167 is equal to 1.417 I2. I2 will just be equal to negative 0.17 divided by the 1.417. And we're going to get negative 0.119. Or we'll just take this to negative 0.12 amps. And if we go up, we'll see that the answer for I2 is basically 0.12. It's very close to it. And if you're wondering why did we get a negative answer, all that means is we just guessed the direction of current wrong. So before we had I2 going this way, like originally, now it just means it goes this way. When you're doing the math though, keep it in its negative form because it'll mess up your calculations if you don't. So just know that yes, the current flowing is actually 119 amps, but we just messed up with the direction. That doesn't really matter. Like now you know. So now what I do is I just take this and I just plug it in back into my equations that have I2. So now we're going to go back up here and we're going to do 10 minus 5, 0.1, negative 0.12 all over 30, and then 10 plus 5, negative 0.12 all over 20. And I can tell you right now, these are going to be equal to the answers. And I can tell you that because since we got this one right and we're plugging it into the right equations for these, we'll be completely fine. So that's kind of how you do it. As you can see, it's not terribly hard and it's not really math intensive. It's just annoying. And sometimes when you get more and more resistors, it gets more annoying. And especially when you have more currents, it's even more annoying because you need more equations. But this is kind of like the harder part of Kirchhoff's laws. And now I'm going to show you an easier one. So I'm going to erase this. Okay. Let's look at this. Let me zoom in. Okay. So the figure to the right shows a circuit diagram. Determine the current, the potential of the wire A relative to the ground, the voltage drop and the voltage drop across the 1500 ohm resistor. So as you can see, like, oh wait, is this a Kirchhoff cell question? The way to answer that is to look, does it have multiple batteries? And it does. So that means we have to use Kirchhoff's laws. The good thing is here, there's only one current flowing. Over here, there was 3. Right there, right there, right there. Right now, there's just 1. Like, there's only one current flowing, and that's all. So we only need one equation. So it's actually a much easier thing. The question is getting that equation. But we're going to start here. We're going to start at 20 volts. We get bigger. So we're going to do 20 volts. And the current is going this way. That's how I'm doing it. I'm going to erase those lines, but that is how, like, I'll draw a smaller loop. Like this. So 20 volts. Then I'm going to do minus 2000 I. Then I'm going to do minus 30. And the minus 30 is coming from because we're getting smaller. And then I'm going to do minus 1000 I. And then I'm going to do minus 1500 I. Then I'm going to do plus 25 because we're getting bigger. And then here, minus 500 I. And that all equals 0. If you're wondering where this, and this is grounded right here, so it also becomes 0. And so take a second, kind of just think where everything's coming from. I'll kind of like color code everything. So red right here, red's right there, blue right there, orange right here, right there, rainbow right there, galaxy right here, right there. I'll use a highlighter too, right there, and this, and then just live with that and that. So that's kind of where everything comes from. That's color coded. Um, Now we're just gonna solve it. So I'm gonna go back to my pen, and first thing is we can simplify the voltage. 20 minus 30 is negative 10, plus 25 is going to be positive 15 volts. And this all would be, so minus 2000. So basically 2000 plus 1000 is 3000, plus 1500 is 4500, plus 500 is 5000 I2. I mean, not I2, just I. And that's going to be equal to 0. Then we just do 15 volts is equal to 1500. No, I'm sorry, not 1500, 5000 I. And that gives us I is equal to 3 milliamps. You're welcome to do that if you just want to make sure, but I can tell you right now that is the answer. So that's the first part. Now it's going to ask, what is the potential of wire A relative to the ground? So here's the ground. We need to figure out what is the voltage. I'm going to erase. What is the, actually, I'll do what is the volt. So this is what is the voltage here. And to do that, we just need to solve for the voltage drop across this whole path. So let's do that. We know if we look at our equation, it ends at the 1000 ohm resistor. So we're just going to take this part and plug in our I. So we're going to do 20 volts minus 2000 times 0.003, because it has to be in amps, remember that. Minus 30 and then minus 1000, 0.003. And so this is really 20 volts minus, this is going to be, oh, no, sorry. So this is going to be negative 10 volts, and then it's going to be minus 2000 times 0.03, well, 0.003, which is 6. And that's going to be, I'm going to tell you right now, this will simplify to 3, and that's going to be equal to negative 19 volts, which is also our answer. And lastly, what is the voltage drop across the 1500 ohm resistor? So we have our current of 0.003 amps. And so all we really need to do is just use Ohm's law, ver, and plug it in. So we have this as 0.003 amps. And our resistance is 1500 ohms. So what is our voltage? And I can tell you with certainty that's going to be 4.5 volts. So as you can see, Kirchhoff's laws isn't all bad. It's pretty simple. It's mainly Kirchhoff's laws in parallel. When you have like parallel circuits is when it's pretty bad and annoying. But it's nothing like insanely hard. But yeah, so how you could, honestly, I don't have much to tell you on when to use this besides unless you have multiple batteries. Like that's from what I've seen the only time you should be using this. Um, what else is there? You'll take this slow. Like I erased all this here, but you guys remember it's kind of a lot of work. There's a lot of places to mess up, so you kind of just want to take things slow and just make sure you're doing everything right. Try to keep decimal places like to maybe like 3 or 4 when you do them, because I was rounding when I first did this problem off camera. I was rounding to like 1 decimal place, and I ended up getting like answers that were a few decimal points off. So maybe your teachers will mark you off for that. So just be careful about that, because there's a lot of places where a lot of places of rounding will lead to different answers. But yeah, honestly, besides just being careful and practicing, there's not much I really have to say to you guys about this one. I hope this helped, and I'll catch you guys in the next video.